Hello and welcome along to a series of videos that are going to be used to support the Royal Geographical Society resources that I've produced on plate tectonics. This particular set of resources and this particular aspect of them are all about trying to address some of the misconceptions that have arisen and seem to be embedded when it comes to the teaching of tectonics in schools. So, in the spirit of that, can I invite you to take a look at the image on the screen? What are you seeing in this image? Do you see a dog's face, a fox's face perhaps? The reality is that what you're looking at is a duck's beak. And the thing is that once you start to see that in ducks' beaks like that, it's very hard to unsee it. You're looking at a duck, but you're also looking at a dog or a fox at the same time. And I suppose I want to use this kind of like an analogy in the way through for part of the journey that we've got to go on here in this video, in these series of videos. You're not going to come to this with a clean slate. You're going to come to this with some preconceived notions of what is the true and correct way of teaching plate tectonics. So what we need to do is to maybe kind of clear the palette a little bit. Stop seeing the foxes in the ducks' beaks, so to speak. And that's really our journey here, to maybe clarify a little bit of the story of where those misconceptions might have come from, to understand a little bit more about why they are what they are, in order for us to maybe put them out of the way so that we can see, it's not a fox we're looking at, it's a duck. So if you do any kind of Google image search for plate tectonics convection, this is the kind of thing that you will see. Lots and lots of images of those very, very well known, very, very common little diagrams that show these lovely, beautiful, neat convection cells that are occurring in the mantle. And if we go and download one of those, it's going to look something like this there. It's incredibly well organized and extremely neat. Look at how well behaved those convection cells are. And you can see over here that the convection current is rising under the ocean ridge. It's spreading sideways. And we are seeing here the plates sinking down. In fact, we're getting a hint that maybe they melt as they go down into the heat of the mantle because of the fact that they're turning red here. This is the classic of what we will see. But I want you to note actually that through here there are actually some other images as well. Not just those neat little convection cell images. There are other images which show what mantle convection, what mantle dynamics might be like. So I suppose the question is, which of these approaches, which of these diagrams is closer to the truth? Is it the one on the left where we have the classic convection currents and cells? Or is it one on the right where things aren't quite so neat? They're a little bit more chaotic and a little bit more involved. Well, here's the spoilers time. I'm going to be telling you that the one that we need to get rid of is those neat convection cells, that neat convection model. In fact, to use this little analogy, we've got some zombie ideas that need to be slayed. Those zombie ideas that are dead and should have disappeared long ago, but we just can't get rid of them. They're chasing after us, after our brains all of the time. But it's time to slay some zombies. So, which of these two is correct? Well, it's truth time, ladies and gentlemen. Are you going to take the blue pill? Or are you going to take the red pill? Time to decide. Welcome to the real world. Okay, cheesy introduction done. What we're going to do in this series of videos is split them into three, basically. And the first one really going to be taking a look at the evolution of the story up to the point where these zombie ideas that should have died were discovered. And then we're going to look at something of the reason why and how they came about. Then the second video, we're going to go on to take a look at what has replaced that. What are the ideas that have evolved since then? And the third and final video, we're going to take the model that is closer to the truth, and we're going to road test it around a couple of different locations around the world to see how robust and how good the model is. But we're starting off with asking this question: what is the truth? Now, I do want to say at the outset that I'm aware of the fact that the audience here is geography teachers. We teach to exam specifications, we teach to exam mark schemes, and sometimes those mark schemes and specifications don't always seem to give us the degree of flexibility that we might like. Those are legitimate concerns, but what I want to do is maybe just ask us to kind of set that issue aside for a moment while we go through this, because I actually think that getting to the truth of this matters. Now, what we do with this information once we've got it, that's a whole other issue, but we need to have the right information to begin with. And I'm very struck by the concept of powerful knowledge that was outlined initially by Michael Young. Lambert, writing in 2014, says this about powerful knowledge: it's created by specialist communities or disciplines, and these are state-of-the-art epistemic practices. In other words, how we know what we know, epistemology. They're established to ensure that knowledge that created is reliable, that it is truthful, indeed that it is the best that it can be. I want to give my pupils the gift of the best, most reliable, most truthful knowledge that I possibly can. Young goes on to say this about what it enables. It's powerful because it gives the best understanding of the natural and social worlds we have. Helps our pupils go beyond their individual experiences. Knowledge is powerful, he says, if it predicts, if it explains, and if it even enables you to envisage alternatives, that you realise actually that there are more than one perhaps way of seeing this. Finally, knowledge, he says, allows those with access to it to question it, and to question the authority in which it's based. He says you're going to get a sense of freedom and excitement. I agree with him. I think you will. But you can see here that this is all about the pursuit of the best of the knowledge, what is truthful, but it also is an enabling approach, because it enables you to question, to understand better how we have come to know what we know. So it's in that context really that I want to move on into taking a look at what we're going to be exploring here through plate tectonics. And I love this quotation by Konrad Lorenz. He says this: truth in science can be defined as the working hypothesis best suited to open the way for the next better one. It's good, that, isn't it? As I record this, we've just come to the end of 2.5 years of COVID-19 in the UK and across the world. And of course, over the past couple of years, we heard a lot that we were following the science, but we also heard from some people that were a little bit more on the skeptical end of things. We can't even follow this science. What's it even mean? The science always changes. It says one thing one month and another thing another month. It's completely unreliable. Science always changes. Yeah, that's kind of why it's science. But science isn't dogma. Science is our best understanding given the evidence that we've got, given the understanding at the moment, but it is always open to change. And almost inevitably it will change. Sometimes, as we'll see in plate tectonics, radically, you'll get a paradigm shift. Most often incrementally. But for us to understand that epistemological understanding that powerful knowledge can bring, how do we know what we know? I think is a really powerful thing to give our pupils. We're going to do this through the prism of plate tectonics, but underneath it all is this approach that says we're doing science, and what that means is this: we're keeping our minds open to change based on the evidence. Okay, to help give us some structure on the way through with this, I'm going to divide this approach here up into 3 different sections. You'll see along the top here, I've got the expanding evidence base. You'll see along the bottom, we've got the evolving theory. And really what we're going to do is take a journey through time. The foundational idea behind this is that science evolves and changes, and has continued to do so right the way through the history of plate tectonics, including over the past 50 years and up until today, and will do in the future. Science changes, it evolves, but it evolves based on evidence. And we're going to take a look at the evidence from the continents, the evidence from the seafloor, and we're going to bring it really up to date in looking at the evidence from the mantle. And I'm going to tell the story as much as I can of the characters that are involved in this. And I've gone back as much as I can to some of the original source materials, the actual writings and the papers. Because what I want to try and do as I tell this story, which will probably be at the start reasonably familiar to you, is to bring you back into that sense of discovery, the sense of glorious uncertainty as we were discovering and finding out more and more things as evidence became more and more available. And of course, our story is going to start with none other than Alfred Wegener. Now, he certainly wasn't the first person to notice a lot of the pieces of evidence that he pulled together for his theory of continental drift. But Wegener's skills were really in the ability to synthesize the evidence and the ability to let go of previously held things that almost became dogmatic, to come with a kind of an open mind to go, right, well, the evidence seems to be leading to here. This seems strange and bizarre and odd, but if this is where the evidence is going, well, that's where we kind of need to go. This is taken from his paper, which you can get online. You have to do a little bit of digging around for these, but you can get most of what I'm referring to online yourself if you want to have a look. And of course, here is his supercontinent of Pangaea, and the continents have split apart since then. But let's delve in a little bit to his original writings here, things that maybe you're not that used to seeing and dealing with. Because what I want you to do is to get a sense of the incredible attention to detail that Alfred Wegener had as he pulled this together. Now, this is one of his chapters on the geological evidence of the mountains. Mountains of same age, type and geological structure seem to be separated now widely on different sides of the oceans. But in his chapter, he starts down here at the South Atlantic, the first bit to open up, and takes a journey all the way up through to the North Atlantic. Here's what he says here, quoting somebody else, de Toit, correctly held that a special corroboration of drift theories to be found in the fact that the Falkland Islands, although supported on the coastal shelf of Patagonia, here near Argentina, they have no geological connection with that area, but rather with southern Africa. And it's that level of detail as he goes up through this, matching up as best he can. One that particularly caught my eye because it refers to a place that I like to spend a lot of my time on here. We find fragments of an extensive basalt sheet on the northern edge of Ireland. Here is my wife and my dog at the Giant's Causeway in Northern Ireland, the county that I live in. The floor is, or at least was, quite literally lava. It goes from the northern edge of Ireland and Scotland to the Hebrides, the Faroes, to Iceland, across to Greenland. You get this extensive basalt sheet that is now spread apart in different parts of the continents. He then went on to take a little look at other evidence, like glacial evidence, and he assembled this. He says it's in South Africa that the inland ice traces have been most accurately studied. Again, he's drawing from the work of others. Molengraaf in 1898 first found the iced polished bedrock under the old moraine. Later investigations gave us a detailed picture of this glaciation. In many places, he says, one can read the direction of movement from the ice, from scratches on the polished rock, and from this a series of centres of glaciation can be determined, from which the ice spread outwards. In South Africa, he says, the boulder clay lies concordantly along in line with the marine deposits. So in other words, the deposits of the boulder clay are lined up with the marine deposits. The only way to interpret this, he says, is to say that the inland ice terminated here as a floating barrier, as in present-day Antarctica. The snow line, he inferred, must therefore have been at sea level here. This indicates that we're dealing with a genuine ice sheet, not just a mountain glacier. However, exactly the same marine deposits are found in the Falkland Islands, in Argentina, southern Brazil, India, western, central, eastern Australia. However, these traces of the Permo-Carboniferous Ice Age are now widely separated and involve almost half the surface of the globe. Now, he tries, as a thought experiment, to reconcile this if we imagine that the South Pole had been in a different position. If we place the South Pole at the most favourable point, about 50 degrees south, and this curved line on the map here is the equator that would be associated with that South Pole, he says that show the positioning show inland ice traces in Brazil, in India, and eastern Australia lie at a geographical latitude of not quite 10 degrees south. He's then saying that a polar climate would have prevailed almost to the equator. It's clear that he doesn't find that particularly persuasive when he says it's not necessary to stress that this result is ludicrous. The permanence of positioning of the continental blocks has hitherto been treated as an a priori truth requiring no proof. In other words, the previous theory that he was trying to displace, that the continents were fixed, was seen as something that was self-evidently true, that it didn't need to be proved. Wegener was questioning it. He says this, yet in fact it is merely a hypothesis which must be checked against the observed facts. And he says, I very much doubt whether geologists are in a position to adduce a more cogent or better, clearer proof of any of their results than these ice traces provide for the invalidity of their permanence theory. He says that the ice traces basically criticise terminally their theory. We shall refrain here from citing the literature in support of our statements. Clearly a man that was very confident. The obvious needs no backing by outside opinion, and the willfully blind cannot be helped by any means. As far as we're concerned, it is not now a question of whether the continental blocks have moved. Doubt is no longer possible. It is rather a question of whether they have moved in accordance with the particular assumptions of drift theory. In other words, he's saying, ladies and gentlemen, I am right in what I observe. I may not be completely right in how I explain what I observe, but I am absolutely right. There is no room for doubt. Only it turned out there was ample room for doubt. Wegener's theory just didn't gain any traction. There are many, many reasons for that. The intransigence of the original ideas, the fixists' ideas as they were called, that they were the prevalent idea in the geological community. They just simply couldn't open their minds to accepting something that was such a shift in paradigm for them. Other things like Alfred Wegener was a meteorologist, not a geologist. How would he know? And he was a German as well, which in the time of the First World War didn't necessarily align too well with giving him a favourable hearing. A whole bunch of reasons came together. In Wegener's mind, there was no doubt. In a whole bunch of other people's mind, there were plenty of doubt. And the big problem was that he couldn't get a mechanism for what was going on. How does it happen? How does it take place? And because he didn't have a mechanism, his theory was, in the eyes of many, fatally undermined, and there was plenty of room for doubt. But not too long after Wegener started to come up with his ideas, a British geologist, Arthur Holmes, came up with a very, very interesting potential mechanism. And this is where we first begin to see the emergence of the idea of convection and convection currents as the means to move the surface of our planet. This is the original diagram from Arthur Holmes' paper on it. I've taken it here and I've added a little bit of colour to it so that we can maybe see a little bit more clearly what it shows. But remember that he is trying to explain here this notion of continental drift. So according to Holmes, the possible mechanism for moving this is convection currents rising up in the mantle below. Now Holmes inferred that because of radioactive decay there would be heat being generated in the mantle. Turns out he's absolutely correct in that. And we also knew at this stage that the mantle below had some ability to move. That was inferred from some of the glacial rebound, the isostatic rebound after the end of the last glacial period, where the weight of the ice had compressed down the crust, or the lithosphere as we have come to know it, to compress it down and displace the mantle rock underneath. The mantle rock was able to flow. Now, whether at that stage, whether it was liquid or solid but could flow wasn't known. We do now know that the mantle is solid but can flow. It is solid but it is ductile, so over geologic time it will flow. But we knew that the ice had compressed that down, and then since the end of the glacial, whenever the ice melted, the ground isostatically rebounded back up again because the mantle flowed back in underneath. So for that and other reasons, Holmes knew that the mantle could flow, so put together the heat and the properties of the mantle, and he came up with these ideas of convection currents. Now, as I say, at that stage it was broad convection cells coming up underneath the continents, and that's what would split the continents apart. And although we will discover that this is not the correct understanding of what actually happens, it is a tremendous act of insight, because not only does he infer some kind of movement in the mantle, but he also notices a return rate, or infers a return flow of the convection currents, which is related remarkably closely to the idea of subduction that's taking place today. And whenever you get these collisions here, he is postulating a mechanism for mountain building, something that at that stage was still something that was greatly debated. So what we have here is an amazing set of insights from Holmes, and this is the first emergence of the mechanism, the convection currents in the mantle that would move the what we ultimately would come to know as the plates. And then it ground to a halt, ironically enough, given the nature of what they were trying to prove. There was too much resistance, and despite the evidence, and Wegener was looking at the evidence of the geology matching, he was looking at the evidence of the fossils matching, he was looking at the evidence of glacial patterns matching, and even though he couldn't come up with a mechanism, Holmes came up with a proposed mechanism that followed on. Despite that, there wasn't acceptance of it. Now, to be fair, Holmes was inferring this. He didn't have any direct evidence for it. And again, this just seemed so utterly counterintuitive to the people that they were trying to persuade, the majority of the geologists. And so for the next 20 years or so, this theory was largely ignored, until a new source of evidence became available. And that source of evidence was from the seafloor, and it led ultimately to the evolution of the understanding of the movement, that it's not the continents that are drifting, but it's the seafloor that's moving by seafloor spreading, and the continents happen just to be rafts carried passively along by those. But where did that evidence come from? Well, what lies beneath, we're going to see this twice, because in this presentation, in the first instance, Wegener and Holmes struggled to see what was actually happening on the seafloor. We know probably less about the seafloor than we do about the surface of some other planets in our solar system, because we've only mapped, I think, about 15% in high resolution detail of the seafloor even today. So back in the 1920s, 1930s, there was very, very little and limited information coming through about the nature of the seafloor. And as we know, you need to know what's happening in the seafloor to get to the mechanism of seafloor spreading. So how do we find out what lies beneath? It's actually courtesy of the Second World War and some of the technology that was designed then to search for German U-boats underneath the ocean to protect the Allies. And the first of these was sonar or echo sounding to allow us to get a sense of what's down there. If something bounced off and the submarine was there, then you knew that you were under threat. But of course, whenever these people were sailing across the oceans, the vast majority of the time they were nowhere near a threat. But they just kept these records going, and some people were collecting some of these records of the ocean depths as you just sailed across the oceans. And this data started to become available. And it was into the early 1950s, 1952 I think it was, whenever Marie Tharp, a very, very highly skilled cartographer, took some of these data sets that had been collected during the Second World War and after, and started to meticulously take the hand-drawn data sets and hand-draw these profiles across the Atlantic Ocean. And what she discovered as she sat in her kind of cartographic genius as she was doing this kind of thing was that not only was there a central ridge, a middle ridge, a mid-ocean ridge, but there had been hints of that for quite some time. But Marie Tharp discovered that in the centre of that ridge, where you have, right at the centre, you will have central rift valleys. You'll have a very, very long valley sitting at the centre of the ridge. Now, Tharp's genius then was to make some inferences based on that. If you have got a central rift valley, she thought, well, what produces that? And we have some of these on the surface. So the East African Rift Valley, for example, where you have the elevated area coming up and then steep-sided cliffs and a reasonably flat-bottomed valley. The processes that are creating that are tension forces. They're pulling apart. And if you pull the solid rock apart, it will fracture, it will fault, and the central block will drop down. Marie Tharp had found what she thought was evidence of tension forces associated with the middle of this ridge. Now, of course, we know that this is extremely significant. But remember, there was a lot of skepticism. I have to throw in here not just skepticism, but also sexism. Marie Tharp was working for Bruce Heaton, who, when he heard her ideas, completely dismissed them infamously as girl talk. And unfortunately, he didn't take her ideas on board. And it was only a few years later when another person that was working for him was mapping on earthquake focuses in the centre of the Atlantic Ocean. And Marie Tharp took her maps and those earthquake focuses, laid them on top of each other, and they lined up. That what she found was evidence at the central rift valley of earthquakes happening, which was just more confirmation of that tension force. It was only at that stage that Bruce Heaton believed her. And he published her work and didn't credit her, because it was the early 1960s and sexism was still very rife. For the first 2 years, she didn't get named in any of the papers. Now, she was recognised eventually, and it's part of the reason why I want to tell her story here now. Representation matters. But the genius of what Marie Tharp saw and did is a crucial step forward as we nudge this theory forward. And indeed, we're jumping ahead in time a little bit to the early 1970s when Bruce and Marie joined together with an artist to produce this now extremely famous, highly detailed painting for the National Geographic magazine, which to this day I think remains one of the most beautiful and compelling pieces of artistry and indeed science of the ocean floors around the world. And we can see here that this central ridge is now, aside from the continents and the oceans, the second biggest topographical feature on our planet. It dwarfs any of the other mountain ranges that exist on the planet. It comes down here through the middle of the Atlantic, around South Africa, up through Indian Ocean to the Gulf of Aden, then down here to the south of Australia, where we pick it up again to the East Pacific rise, and it comes up here. We now know that it's feeding here through splitting off by High California, creating the Gulf of California linear sea, which is slowly but surely splitting California off from the rest of the North American plate. But at that stage, the genius was the ridge and the Central Rift Valley. Which brings us to our next character and another story to do with the Second World War. This is Harry Hess, a geologist from America who served in the US Navy during the Second World War, and like many of the others was collecting all of this data and storing it. Even when he wasn't being involved in some of the military and naval operations, he was just collecting the data. And he had already noticed independently that there were these central or these mid-ocean ridges, and he'd also noted the deep ocean trenches. In fact, he was involved in the Mariana landing over at the Marianas Trench. So he noticed the ridges and the trenches, but it was whenever Marie Tharp's work was published that gave him an impetus to go and look again at his work with fresh eyes. And he came back to the work and came back to Arthur Holmes' idea of convection. So let's take a look at his paper and enter in a little bit to the story of what was happening there. This is the paper published now. We're in 1962, and the years are going to go by very quickly now as we get towards the crystallization of the theory in around about 1967-68. And this is a piece that he wrote on, a paper he wrote on, titled The History of Ocean Basins. So this from his introduction. The birth of oceans is a matter of conjecture. We don't know. The subsequent history is obscure. The present structure is just beginning to be understood. Fascinating speculation on these subjects has been plentiful, but not of much of it predating last decade holds water. Now, from what I understand of Harry Hess, not only was he a very gifted geologist and thinker, he was also a very compelling communicator. He knew how to work a crowd. He knew how to try and persuade over the skeptics. So in writing this, he uses this wonderful phrase. He says, I shall consider this paper, the one he's writing, as an essay in geopoetry. Long ago, he says, Holmes suggested convection currents in the mantle to account for a deformation of the Earth's crust. Nevertheless, mantle convection is considered a radical hypothesis. It's not widely accepted. But here's where the geopoetry comes in. He's basically about to say to everybody, listen. I know I'm going a wee bit beyond the bounds of what people normally think here, but just run with me for a moment, will you? Because here's what I think you'll find. If you accept this to be true, wait till you see how much explanatory power it has. Here's what he says. If that the convection currents were accepted, a rather reasonable story could be constructed to describe the evolution of ocean basins and the waters within them. Whole realms of previously unrelated facts fall into a regular pattern, which suggests that close approach to satisfactory theory is being attained. See how he's trying to convince, how he's trying to win people over. Just go with me here. Geopoetry, all right? So what did he find? He said the unexpected regularities in the Earth's topography, the ridges and the trenches, might be attributed to the idea that the continents move to positions dictated by a fairly regular system of convection cells in the mantle, as per Holmes. The ocean ridges could represent the traces of the rising limbs of the convection cell, while the circum-Pacific belt of deformation, that's your trenches, and volcanism, represents the descending limbs. The continents do not plough through the ocean crust, impelled by unknown forces, as suggested by continental drift and Wegener. Rather, the continents ride passively in the mantle material as it comes to the surface at the crest of the ridge, then moves laterally away from it. A beautiful simplicity to it. And you can see how he's leaning in into the ideas of those that have come before. And I don't know, I'm just speculating here. I wonder did he consider that might give him a little bit more credence and believability. And in the paper he includes a theory that, or a hypothesis that he had come up with to explain how you might create new crust at the ridges. Because if you create magma by melting here, you can create new crust. And you put all of that together and you start to get this process that eventually became known as seafloor spreading. That you get a new material created here at the ridge. Because it's young and hot and buoyant, it will rise up. But as it cools over time, it will slide away down off the side of the ridge. And you will get this age progressive movement away, displacing the material by this process that we will ultimately come to call ridge push, pushing away from this. And in his paper, he came up with this possible geometry of a mantle convection cell. you'll see here that one of the differences between him and Holmes was that Holmes thought the convection would come up in broad areas beneath the continents. Hess said that they're going to come up in these narrower areas beneath the ridges under the oceans, and then will spread out and sink all the way back down again. Now that looks incredibly like those Google image search images that we did at the start, doesn't it? At the end, he summarises, the mantle is convecting, it's at a rate of a centimetre per year. These convecting cells have rising limbs out of the mid-ocean ridges. The rising limbs coming up under the continent areas move the fragmented parts away from one another at a uniform rate, the same rate either side. So the median, or the central ridge, formed in the middle of the Atlantic. The continents then are carried as passively in the mantle with convection, and they do not plough through the ocean crust. And he finishes by saying this: in this chapter the writer has attempted to invent an evolution for ocean basins. It's hardly likely that all of the numerous assumptions made are correct. Nevertheless, it appears to be a useful framework for testing various and sundry groups of hypotheses related to the oceans. And it is hoped that the framework, with necessary patching and repair, may eventually form the basis for a new and sounder structure. This is science. This is science. The best hypothesis at the moment to create the conditions for the next better one to take over. You really get the sense of evolution that's going on here for this. So where does this leave us? Well, Hess is suggesting a process that is compatible with the evidence. It was Robert Yates who came up with the phrase seafloor spreading that came attached to Hess's idea that the seafloor is moving, and the evidence is compatible with that. Stewart, Turcotte and Olson in 2001 said this: it was immediately recognised that the new hypothesis of seafloor spreading is entirely consistent with the older idea of continental drift. In the process of seafloor spreading, the continents are transported with the ocean floor as nearly rigid rafts. And this realisation, they say, was a critical advance in defining the role of mantle convection, because it shifted the emphasis away from the continents, as Wegener was suggesting, to the seafloor. The drifting blocks of continental crust came to be seen as merely passive participants in mantle convection, whereas the dynamics of the process were to be found in the evolution of the ocean basins. So here again is our schema. This expanding evidence base that started with Wegener pulling together all of the evidence in that meticulous, incredible detail of the continental evidence of rock type, age and structural orientation, of the different fossil distributions, of glacial evidence and things like this, came up with the notion of continental drift. It was Holmes who then came up with the idea that convection currents might be responsible for that, and then this plethora of seafloor evidence that started to come through after the Second World War brought us to the theory of, or to the hypothesis, I should say, of seafloor spreading. And Hess drawing again on the hypothesis that Arthur Holmes had put forward, reignites this convection current theory. But we needed some independent evidence that the seafloor was actually moving, and it didn't take long for that to come. For this, we need to come to a couple of British geologists, Vine and Matthews, who took some data that had been collected from another device from the Second World War to try and find these German U-boats, the magnetometer, which could find the magnetic submarines underneath. And again, as the ships were sailing across the sea, they were just gathering these data over and over and over again. And what the data revealed was something very, very interesting. As you move from a central ocean ridge, either side, as you move away from the central ridge, the magnetometer will come through a band of magnetic field that is slightly amplified. Then it will come through a band of magnetic field where it's slightly weaker. Then slightly amplified, then slightly weaker, over and over and over again. And crucially, this band was symmetrical either side of the mid-ocean ridge. Again, although they didn't call it geopoetry, in an act of geopoetry, these two gentlemen made some assumptions that absolutely weren't widely accepted at the time. Assumption number one, let's assume for sake of argument that seafloor spreading, as suggested by Hess, is occurring, number one. Assumption number two, let's assume that the Earth's magnetic pole changes its position from the North Pole to the South Pole and back and forward over time. Now, neither of those was yet established, but if we assume those to be true, said Vine and Matthews, what do we discover here? Actually, we're discovering the start of some of this independent evidence for seafloor spreading. Because imagine here, in the case of this one, that you've got the seafloor here with this slightly amplified signal, as you're pointing towards this. That shows us that at this time, whenever the basalt was forming the seafloor, the magnetite within it, while it was still liquid magma, the magnetite orientated itself with the direction of the magnetic North Pole. Then, as the rock began to cool and crystallize and harden, that orientation was locked in. And it becomes a record. And whenever the boat goes over the top of it, that gives a little bit of a boost, just a little bit of a boost to the Earth's magnetic field, which can be measured by the magnetometer. Then, you're over here. You have got a period of time whenever the magnetic pole was at the South Pole. The magnetite there, when it comes out, orientates to the south, and as it orientates to the south and cools and hardens, locked in. So what you basically have is this record, these tape recordings of the change over time. If we look at it like this, we can see how the ship goes over the top, towing the magnetometer. And what we can get here is this record of this change. But also crucially, what Vine and Matthews discovered was an incredible amount of symmetry either side of the ridge. Symmetry yet again. Which absolutely is consistent with this theory of this new seafloor being created at the ridge, the tension which is indicating that there's something pushing them apart. And as they're pushed apart from the ridge, the symmetry is the same either side of the ridge. This was corroborating evidence for the process of seafloor spreading. The final piece of evidence, just to get locked in, came from the age of the seafloor, and this came from this ship in particular, the Glomar Challenger, that did a lot of drilling down through the sediments on the seafloor to the actual rock beneath to be able to date the rock. And what we discovered was this pattern, now a very, very famous pattern of the age of seafloor. Now, you're probably well used to this, but as recently as the mid-1960s, this was ultimately a paradigm-shifting shock revelation. The symmetry, the pattern, the consistency, and all of a sudden, very, very quickly, the theory of plate tectonics coalesced. The weight of evidence built up so much that it was increasingly difficult for the skeptics to remain skeptical. So if you take a look here at the centre of the Atlantic Ocean, for example, you have got here a central ridge, a mid-ocean ridge, with a central rift valley. That central rift valley seems to suggest the tension forces pushing this apart. You have got this increasing age and the symmetrical pattern here either side, which shows that the processes that are producing this are likely to originate in the ridge and are pushing them aside. Over here in the Pacific, you've got the ridge and you've got the trenches here, which are consuming the old seafloor over time. We discover actually that the oldest seafloor in our planet is not much older than 250 million years. Which, when you consider the oldest rock that we have on our planet can be billions of years old, that's relatively very young. So we see that although the continents seem to be quite permanent features, although they move around and collide and rip apart, the seafloor seems on geological time to be quite transient. It's created here, it moves here, and it sinks here down into the mantle again to be recycled. So you get these relatively transient, only 250 million year old seafloors, and the evidence just came together. and the theory of plate tectonics was nearly there. One final element was how these ridges and the trenches fit together. This is a map just of the constructive and destructive margins on the planet. And you can see here that there are a number of gaps, a number of places where, well, we probably now know what goes in those places. But at this stage, the geologists weren't too sure. What is it that connects all of these? Is there any way that we can do so? And we come to our final character in these early stages of plate tectonics, Tuzo Wilson. And this is his paper in 1965, A New Class of Faults on Their Bearing on Continental Drift. He says this: many geologists have maintained that the movements of the Earth's crust are concentrated in mobile belts. That's the margins, as we later come to know them, which may take the form of mountains, mid-ocean ridges, and major faults with horizontal movements. These features and the seismic activity that along them often appear to end abruptly. This is puzzling. The problem has been difficult to investigate because most of these terminations lie in ocean basins. And here is the sketch from his paper that I've marked on here in green, the spreading ridges, and in red, the collision zones with the gaps in between. This article suggests that these features are not isolated, he says, that few come to dead ends, but they are connected into a continuous network of mobile belts around the Earth, which divide the surface into several large rigid plates. Here come the connections that he was proposing. It was this new category of fault that connected together all of the different plate margins. It's called a transform fault. Now, here's again from his original paper. You'll be familiar with this if you know anything about the mid-Atlantic ridge. But basically these transform faults can join together all sorts of configurations of constructive and destructive margins. And another little sketch which shows how this helps to connect together the broken up elements of the mid-ocean ridge. I love this photograph, or this sketch that he has done here of the San Andreas Fault. The orientation is a little bit different, so I've coloured this again so that you can maybe see it a little bit better. But what I love about this is you can see down here the East Pacific Rise, and up here the Juan de Fuca Rise. The small little plate here of Juan de Fuca, you've got Washington DC here where you've got this subduction zone occurring. But for the thousands of kilometres in between, you've got this massive big transform fault, the San Andreas Fault, which basically is a transform fault connecting this ocean spreading ridge with this ocean spreading ridge. And this connection, these connecting faults, allowed us to bring this all together in this global pattern. And what we were able then to do, and what Tuzo Wilson was able to suggest, is that the lithosphere of the planet is broken into a series of plates, rigid plates, that are connected to each other by those three main types of faults, the three main types of boundaries. Your constructive or divergent, your destructive or convergent, and your conservative or transform. And that was the last element for the plate tectonics theory to come together. The seafloor spreading and the evidence that came to support that. So Davies and Richards summarise plate tectonics at this stage like so. Plate tectonics is a global theory of global tectonics powered by subduction, more on that later, in which the lithosphere is divided into a mosaic of plates which move on and sink into the weaker ductile asthenosphere. Three types of localized plate boundaries form the interconnected global network. New oceanic plate margin is created by seafloor spreading at mid-ocean ridges, and old oceanic lithosphere sinks at subduction zones, and the two plates slide past each other along transform faults. The end. And they all lived happily ever after. Or is it? Up until this point, I have probably outlined the understanding of plate tectonics that most of you will have, because it's the one that's out there that's the most common one. And it certainly was a form of the theory. It certainly was something that was showing tremendous insight, and people pushing against the skeptics and pushing against those that were stuck in, arguably their dogmatic views. This was the story of science evolving in response to the evidence. But the problem for us is the story didn't stop there. For some reason, popular understanding seems to have done. But as I've tried to do by telling you this story, this was the story of evolution up to this point in around about 1967 or so, whenever you had this massive paradigm shift, whenever people finally came to accept plate tectonics as a theory. But it's absolutely true to say that since then, plate tectonics has continued to evolve. And yet our understanding seems to have got stuck in the past. So having established some of the groundwork, the parameters here, that what truth is in science and how the theory evolved up until this point, our next job in the next video is to ask the question, what came next? What additional evidence started to emerge, and how did the theory tweak and transform? Let's continue to do science as we answer those questions.